going to be about in situ TEM, especially one specific variant of in situ TEM called Environmental Transmission Electron Microscopy. And just to give you a brief outline of what I'll be talking about today, first I'll start out with a bit of history. I won't dwell on that too much because history is always a bit boring. Then I move on to the concept, show you a bit of how the instrumentation works, and then I'll move on to a bit of experimental considerations that you need to do before you do your environmental TEM experiments. Then I'll move on a little bit about how the imaging in a gas atmosphere, or how imaging in a gas atmosphere affects the microscope performance with respect to resolution and so forth. And then that will hopefully bring us about halfway in, and then the second half I'll try to outline these concepts that I've shown in the beginning with a couple of applications. I've shown some of them here. I don't know. I might skip some of them or save some of them for tomorrow. And tomorrow I'll go much more into detail, but with a fewer examples, mainly related or revolving around catalysis. So, first of all, it might be a good idea just to make sure we all know what we're talking about here. So, what is in situ microscopy? Well, that certainly depends on who you ask, because there are a lot of people doing what they call in situ electron microscopy. My former supervisor, PhD supervisor, he defined it this way: the class of experiments allowing observations of materials' dynamic response to an externally applied stimulus as it happens inside the microscope. Now, that's a very heavy sentence, but it actually outlines very exactly what we're trying to do. We're trying to interact with our sample and see how it reacts to the way that we interact with it. And that could be via various routes. Furthermore, you can get feedback from the samples as they are exposed to various kinds of stimuli, and you can. This is of course again. Oops, sorry, pointing on the wrong one. This is again related mainly to catalysis studies. You can establish structure and functionality relationships of your materials when exposed to certain stimuli. So what kind of information is that we're trying to obtain? Well, first of all, we're trying to get high resolution information. Of course, that's really the game in transmission electron microscopy these days. Secondly, we're trying to determine dynamic responses of the materials as they're exposed to reactive gases. So, for instance, now this up here is a simulation. This down here is the real image, and this is not an in situ image, by the way. It's just a standard operation corrected images. But how would this surface change? How would these steps and kinks change when exposed to different reactive gases and at different temperatures? So again, surface structure of materials in various environments, and also the morphology of the materials, how it changes. So I'm from the catalysis world, and if you look at a typical reactor, it looks something like this. You have a tube that's heated to anywhere between room temperature and maybe even higher than 1,000 degrees, which I put here. And usually the pressure in here is tens of bars, hundreds of bars even. That's of course nothing that we can reproduce in the microscope for the time being. So if you take a closer look inside the reactor, you get these little pellets, which are maybe on the order of 10 millimeters in size. And if you take an even closer look, in most cases you'll see that the active phases are these little metallic particles, which are supported on usually an oxide material, could also be carbon. And if you move even closer, you'll see that you have these little active particles, and this is actually an in situ micrograph recorded at 500 degrees C in a hydrogen atmosphere. This is a nickel particle used for steam reforming of methane, supported on a magnesium aluminum oxide support material. Had we been looking at this little particle in high vacuum, this would for sure be an oxide. Now that's not the case, and we can easily see everything's identified here. I don't know if you can see the lines here, but you can. So you have the 001 facet up here, you have the wolf point up here, and everything matches perfectly to metallic nickel, which would not be the case in a conventional microscope. So what we're actually trying to do is to see what are the active phases during or when exposed to the reaction environment. So when we do that, conventional electron microscopy, which is carried out in high vacuum, doesn't always tell the full story, because most of the samples that we're looking at are not in the typical environment. Most samples that we're looking at do not operate in high vacuum. They operate in ambient atmosphere or in a catalytic reactor at high pressure. So what we want to do is we want to expose them to an environment that's more typical for the one they're working in, and see how they dynamically respond to changes in this environment. The image over here is, of course, a model. The sites you see indicated here are also called B5 sites, which are believed to be the active sites for nitrogen decomposition for ammonia synthesis. This threefold hollow site and the bridge site you have up here. Nitrogen, the dinitrogen molecule can adsorb here and be decomposed into two nitrogen atoms, which can then combine with hydrogen and form ammonia. Second of all, we don't have any temporal resolution in conventional microscopy. We can't really change anything, so the situation usually stays quite stagnant. So we don't see any effects of time. So doing in situ microscopy is essential for establishing these structure-activity correlations. And if you look a bit back in history, and again this is from the catalysis world, from the 1950s up to about the 70s, most catalysis studies were done by trial and error experimentation. If something didn't work, you tried something else. And okay, you can improve your performance. This here shows the relative activity by volume of a hydrodesulfurization catalyst. And you can see, okay, just by doing regular trial and error, you take the best catalyst and you try to do something to that, and then you make it better. But that has kind of a limit. Then in the 70s, people started to do a lot more in situ work, and then you can again start to increase your activity, and you can really understand what's happening during the reaction. And then again, you see you get up what's called the second S curve up here, because people really started to understand the reactions as they occurred. There are a bunch of in situ techniques, among others. In situ XRD is probably one of the most used. It's great for phase determination, and it's good for large areas. Same goes for XAFs. In situ XAFs is also one of the heavily used techniques, and Fourier transform infrared spectroscopy. Gives you the coordination, the chemical bonding. The drawback with these two techniques is that they give you average values. You don't get any local information. You put your sample in, you see what happens, but you can't see on a local scale. Now that's what you get from in situ TM. You can probe a single nanoparticle as it's exposed to certain environments. And I'm sure that I just put etc. here because I didn't want to insult anybody for doing techniques that I hadn't put up here. So, as I mentioned, in situ TM is a quite broad term. There's a bunch of stuff that you can do. I think we saw yesterday, Roel talked a little bit about the conductivity measurements, which you can do STM inside the microscope. You can expose it to light. I'll talk a little bit more about that tomorrow. You can do nano indentation. This is heavily used in the oil industry, where people see how much pressure can certain types of materials take before they crack. You do FIBET, and I'll tell you what this acronym means a bit later on today. And of course, heating and annealing, which is probably the most used in situ technique. And then finally, environmental TM, which is what I'm going to be talking about today. But certainly there are many flavors, and there's probably a bunch more than I put on this slide. Just to give you just a quick look into some of these other techniques. This is a Swedish company called Nanofactory who makes this very nice atomic force microscopy holder for the TEM, where you have your little tip sitting here, and you have your sensor over here on the other side. And this is the first commercial holder with an incorporated force sensor, so you can actually indent with this as well, and do a nano indentation. The drawback is that the price is fairly steep. What you can do with this kind of a holder is you can take your little needle, you can put your nanowires on it, then you can bring these the tip and your sample into contact, and then as you see up here, you have your wire sticking out here. It's fixed on the other side. Then you can actually, by applying a potential, you can deposit little drops. You can see you have drops inside the nanotube, and you can deposit these in a controlled way, which is quite neat. In this case, it's copper indium encapsulated in carbon nanotubes. You can also do force measurements. I think I just skipped this one because Raoul talked about this yesterday. But also again, you can deposit stuff, and you can see how the stress changes if the tube is filled or if it's empty. Just a quick word on resolution here. So why do we actually need to go to these super high aberration corrected high resolution microscopes? Well, again, coming from the catalysis world, many of the elements, the active elements that we look at are the transition metals like platinum, gold, or palladium, platinum, and silver, gold, and maybe more of these down here, chromium, iron, nickel, and copper. And you can see many of the lattice spacings you can easily resolve in a conventional, at least a field emission microscope. But when you get down to some of the other ones, it becomes a bit more tricky. Most of the field emission microscopes are in this range, about 1.5 angstrom, something like that. And when you get down to these smaller spacings, you cannot resolve them. So you need to go to the aberration corrected machines. The second benefit of the aberration corrected microscope is that you don't have what's called surface delocalization. Over here, I forgot if this is actually silver or gold. It's one of the two. You see a nice aberration corrected images where you can clearly interpret the surface. And over here you see the same surface imaged with the corrector on and with the corrector off, and you can clearly see it's quite difficult to interpret the surface structure of the non-aberration corrected image, whereas you can easily see the positions of the individual atoms in the aberration corrected image. So that's really one of the benefits of having an aberration corrector on your microscope, that you can start to interpret the surface structure of materials on a one-to-one basis. So just a quick historical overview of ETEM. Actually, ETEM, or gas stages, was proposed already by Jan Struska back in the 40s. I don't think he ever made any, but he at least proposed the idea. Heating stages, the earliest reference I could find was 65 by Hirsch and Howie. And in the late 60s, and there's an older conference paper than the one I put here, but I just couldn't find it. In Japan, which is probably the pioneering country of this kind of work, they developed this, which is actually an in situ cell that can be used in any microscope because it's built into the holder. And this is actually on the same concept that we're using today, where you use pressure limiting apertures down here, and I don't know if the upper one is marked. It should be one up here as well. So you can limit or confine a gas around your sample while still maintaining high vacuum in the rest of the column. And you can do heating as well by having this is just a joule heating. Oh, sorry, this way. It's the joule heating. Then you have a thermocouple the other way to measure the temperature. This kind of a setup was used heavily by Baker and Harris in the 70s and 80s to study carbon deposits and sintering of nanoparticles. The concept that we use today, or the setup that we use today, is the differentially pumped system, which was pioneered by Ed Boyce and Pradeep Ghai. And if you want to see all the details of this, you can check out this Electron Microscopy paper, which has all the details of the first column, which was built in this way. And this is also the way that more recent microscopes have been built. And recently, just to give you a quick overview here, you can see that the resolution has gradually gone up. Well, ammonia, that might be the reason. This was the first microscope discussed in the article I showed on the previous slide, where you can. This is a Lab 6 instrument, as far as I recall. And back in 99, the machine at Halder Topso was installed, which was the first field emission gun environmental TEM, and all of a sudden you could get down to these very nice resolution. A few years later, Peter Croce and Renu Sharma made their FBI Tech9, which was a home-built instrument, which improved the resolution slightly. And after that, the whole FBI Titan generation came along. And when you ask FBI, they do not want to quote any resolution numbers on the ETEMs. So I only put hopefully good. And as you'll hopefully see from the slides later on, yeah, it is quite good. But there's a couple of them now. And actually the ETEM at Stanford, which was delivered last year, was Titan number 100. So now we talked a bit about what it is. So it's also important to know what it's not. It's not UHV science. The chamber inside your microscope is not a UHV chamber. It's not meant to be. You can make modifications if you really want to, and you can make a UHV chamber, but it's complicates things quite a bit. We can have a high degree of control of gas composition inside the sample region and the temperature for that matter, but it is not a UHV chamber. It's also not operando spectroscopy and microscopy. We cannot go to the conditions that you find in a reactor, which is typically hundreds of bars. We can only go to a few millibars. and it's not large-scale science. We are only looking at, it is conventional microscopy for that matter, we are only looking at very, very small samples. And that also means that kinetics and reaction products are typically very complicated to measure because you have very small amounts of sample within your sample region. With that said, if you look at a conventional microscope, the pressure in there is usually on the order of 10 minus 8 millibars. In the ETEM, it's about 10 to the 1 to the first millibars. On a bench scale reactor, it's somewhere around atmospheric pressure 1 bar or something like that. And in industrial reactors, you have hundreds of bars. So if you look at these numbers, actually, we've gone most of the way. We've gone 9 orders of magnitude. There are only 4 orders of magnitude left. So with a bit of engineering, who knows? And here you have what the instrument at DTU looks like. This case up here hides all the pumping systems. This is a schematic of how the instrument looks. If you look at the top part of the microscope, it's basically a conventional Titan column where you have your field emission source. In our case, we also have a monochromator on it. Then when you move down, actually I'll put this one here because, well, let's start from this point because that's where we leak the gas in. We leak our gas into the sample region. We have a sample here. Then we have the sample confined by 2 pressure limiting apertures. Now these are one of the modifications made to the column to be able to allow us to have a gas inside the column. This gap here between these 2 pumping apertures is about 7 millimeters. So it's not to scale, obviously. We then let the gas get a stable pressure in the sample region. We let the gas leak out through these apertures, and then we pump it out again. We do that twice. That means that we can go from about, say, 10 millibars to 10 minus 3 millibars to 10 minus, I think it's 10 minus 5. And then at the way top, you basically see no change. So the gun is completely safe in this setup. If you notice, there are dummy channels here on the other side because you actually, to make this modification, you have to drill holes all the way through your objective lens. And if you do that in a non-symmetric way, you completely change the magnetic field inside your lenses. So you have to drill channels in a symmetric fashion, otherwise you completely destroy your objective lens. And that is not easy. So the first step here is, or the first pumping step is by a turbomolecular pump. Same for the second one. And the third one up here is by an ion getter pump. And what's really important to notice is that in this column, there's a direct line of sight from your electron source through your sample to your detector. The only obstructing things are the apertures, which is just a tiny hole. So there's a direct line of sight, so gas can actually leak all the way through the column. But because it's pumped away in these steps, you don't see a difference at the gun region. Of course, there's also the other way of doing it, which is the window design. This has many advantages and a few drawbacks as well. In the window design, what you do is you have a tiny gap surrounded by electron transparent windows. Which may be easier to see on the other slide here. There's a few 100 microns here. You have spacers, so you can have your samples sitting inside here. And in this kind of setup, they have actually demonstrated up to atmospheric pressure within a TEM. The drawback is that EDX is very complicated and sample fabrication is very complicated, whereas the other setup is much more versatile. But having both this would be the best of both worlds. Here you can see how the gas is leaked in through tiny channels here in these MEMS fabricated devices. You leak gas in on one side over the sample and pump it out on the other side. So you have a flow of gases in your system. All in all, this is what it looks like, or if you make a schematic of it, you basically have a little tiny reactor. You can leak your gases in. You have your sample lying here. You can heat it. You can measure the temperature. You can measure the pressure. And then, of course, you have the apertures where you can shine your electron beam through and you can get an image. On top of that, at least on our setup, we have a capillary sticking into the objective lens right on top of the sample, so we can measure the exact gas composition using a mass spectroscopy inside or just on top of the sample region. So basically, it is not a cell. It is just the inner part of the objective lens. So usually when I give this presentation in a class, I would ask a question here. So I think the audience might be a bit too big for that, so we'll maybe skip straight to the solution. But consider if you have 10 millibars of gas, which is a typical working pressure for your E10, how thick a sample of, say, carbon and nickel does that correspond to? Any guesses are welcome here, but you can assume that room temperature maybe. These are just the standard textbook numbers. I put 5 millimeters, that should actually be 7 millimeters. But let's skip straight to the solution instead. So if you assume, and that's probably quite safe with the gases we're using in the microscope, and considering that the pressure is quite low, it's probably fair to assume that we can consider it an ideal gas. So we can just reorder the ideal gas equation a little bit, and we can calculate the density within our microscope at 10 millibars. It should be about 0.4 moles per cubic meter. In the sample region, so this should again be 7 millimeters, not 5, but doesn't change the numbers over much. So in the sample region, we have about 2 times 10 to the minus 3 moles per square meter. For nickel, the density is about 1.5 times 10 minus 5 moles per cubic meter. And if we divide these two numbers by each other, we can see that this gas density, these 10 millibars, corresponds to a solid sample of about 10 nanometers. So basically, that is perfect for high resolution microscopy, and we often image samples sitting on top of a 10 nanometer thin film, and we get nice high resolution images, no problem. Now, there's one thing that we haven't considered here. When we look at a conventional sample, it's always sitting at the eucentric plane of the objective lens. That's not the case for the gas. It's spanning the entire pole piece gap. So you basically have scattering of your gas molecules throughout the pole piece gap here. I'm not going to get much further into this because honestly, we have no clue what's going on. We're trying to find out how exactly this affects resolution at the moment. But just so you know, your sample is no longer a thin sample. It's spread out over quite a big gap. So some experimental technicalities and considerations. Some people have already asked me previously if you want to put hydrogen and nitrogen in there, or sorry, oxygen and hydrogen at the same time, and that's probably a bad idea, even at these low pressures. So you do have to think your experiments through a little bit before you actually carry them out. One of the most important things is feeding gas into the E-cell, because in most cases you want to heat at the same time as you have gas in there. So due to the very limited power available in TEM holders, just having the flow of gases is going to drastically affect your temperature. And any of you who've been working with TEM holders, you know that when you change temperature, you can forget about high resolution microscopy because everything's drifting all over the place. So if you do not have a very steady flow of gas around your sample, you're screwed. So you need to be able to control the flow very accurately. The flow inside the cell is very low compared to bench scale reactors. We only flow maybe a few normal milliliters per minute, so the flow is extremely low. That means that we're also very sensitive to contaminants or leaks in the system. So we need to have a high degree of control of this flow into the setup. Oops, sorry. We do that by using digital mass flow controllers, so we can down to the most accurate ones you can get, I think. So you can control down to about 2 normal milliliters per minute. You can control the flow with 0.1 normal milliliter per minute. And also you have to consider, do your gases react with each other? For instance, oxygen and hydrogen would not be such a nice combination. And also, of course, do they react with the internals of the microscope? The inside of the objective lens is coated with various things, and you might want to make sure you know what that is and make sure that your gas does not react with that before you do your experiment. This is how our gas inlet system looks. 9 out of 10 experiments are done in hydrogen, so we want hydrogen, and most of the rest of them are done in oxygen. Then we also have a couple of inerts and other gases that we can imagine people using on our system. We have our high pressure lines coming in from the top here. We have the 7 flow controllers with these 7 gases mounted. We have up here the manifold where the gases are mixed after coming through the mass flow controllers. Then we leak it into the microscope over here where we can measure the pressure just before it goes into the microscope. And if we want to get a good mixing, we would increase the flow to a very high level and then just remove most of the gas to make sure we have a nice mixing in the manifold here. We do that by having a pressure controller on the manifold. And then we can just pump out much of the gas this way. Here we have a bunch of filters. I just indicated the active carbon filter, but we have a bunch of filters that we can use to make sure the gas is as clean as possible before we introduce it into the microscope. We also have other auxiliary lines, so if this is if you want to use something else in this, we can just add it on the fly. You also want to make sure that your gases are very clean. As I said, just a low degree of contamination is critical or could be critical to your system. We normally operate maybe at a few hundred pascals and a few nmLs, normal milliliters per minute of gas. So what we do is constant online monitoring of the gas composition. So leaks are crucial. Desorption from pipe walls from earlier experiments. So you want to group your experiments. You don't want to do an oxidizing experiment one day and in the afternoon you do a reducing experiment. Forget it. It's more or less impossible. So what you would want to do is you would want to group your experiments. So 1 week you do an oxidizing experiment. The next week you would do a reducing experiment. And then over the weekend you would bake out your system to make sure it's nice and clean. You also want to make sure that your gases are compatible with the O-rings, and you should also know that there's a bunch of O-rings on microscopes today, and you do have a leak in there as well. They are not completely tight. On our microscope, we have an in-situ plasma cleaner for general housekeeping. So when it gets really dirty in there, we can just leave it plasma cleaning over the weekend. And we could also do plasma cleaning while we have a sample in there. But you want to be a bit careful with that because plasma cleaning does or can affect some samples quite severely. Quite often when people do reactor experiments, they would use carrier gases because many labs, they don't allow you to flow 1 bar of say hydrogen. So they would dilute it in an inert, say helium or argon or nitrogen or something like that. We prefer not to do that. We prefer to stick to the pure gas because we don't want our total pressure to become too high. Holders is of course one of the most critical aspects of doing in situ experimentation. Here I've shown one of the Catan holders, a double tilt heating holder. Obviously provides heat to the sample. When you just do conventional microscopy, you don't have to be too careful about what your sample holder is made of. But when you start to do ETEM, you might want to be a little more careful because all of a sudden you could have an oxidizing atmosphere in there. So whatever is inert, this is the furnace you see here, which is inert or could be inert under vacuum conditions. All of a sudden, if you have an oxidizing agent in there, your filament, which is inside here, could oxidize and your heating holder is dead. Furthermore, the power you get from such a holder is very limited, so just tiny changes in the flow can be detrimental to your temperature. The downside of such a holder is that it's quite bulky, so when you heat it up, there's a lot of drifting. And as I mentioned before, if you have done heating experiments before, you'll know that you have a lot of drift when you heat your sample. There are also alternatives that people are exploring, primarily MEMS devices, but also laser heating, where you expose or have a laser beam on your sample to heat it up locally. And on that very note, I think I'll add, this is one of the heaters that we're using, a MEMS device. You have a 4-point contact, you have a little coil going in here. The main benefit of this type of system is that it's only a very, very tiny region. This is only a few hundred microns across. So it's a very tiny region that you're heating, so there's not so much that can drift during your heating ramp. Second thing is that because it's so small, you can heat up very quickly. Luis told me that you have actually one of these holders here in the lab, a prototype holder, and I've heard that would easily heat to 1,000 degrees in a second or so. So you can do very high heating ramps and I guess also cooling ramps with much less drift than you see in the conventional holder. Grids also all of a sudden becomes a completely different thing because normally you choose grids based on complementarity of your sample. So if you were analyzing a nickel sample, you would use something other than nickel as your grid. If you're analyzing a copper sample, you would obviously use something that doesn't contain copper. Conventionally, we all use copper grids, and I think I found on one of the grid manufacturers' web page that 95% of the grids that are sold are copper grids. Copper oxidizes in an oxidizing atmosphere, obviously, and at fairly low temperatures. So if you want to do an in situ experiment, copper grids is usually not good. So you want to really think what kind of grid you're using, and this is going to be compatible with the atmosphere that you're going to have in your microscope. So you need to consider the temperature. Is a material prone to oxidation or any other kind of reaction with whatever gases you might have in there? Will react with the gas phase inside the microscope. Another thing is that some materials have a significant uptake of gases. For instance, titanium takes up quite a lot of hydrogen, and it will become brittle. I found a quote here on one of the grid manufacturer's webpage. Use molybdenum grids for TEM studies when high temperature and inertness are needed. Yeah, that's all good if you're working in vacuum, but if you're working in an oxidizing atmosphere, you start to form volatile molybdenum oxide species, and you're not going to get your grid back out of the microscope. We tried that once, and it just didn't come out again. This is what happens. This is the copper grid, just treated in oxygen at 500 degrees C. This used to be a very nice graphene sample, but along the grid bars, you started to form filaments of copper oxide like these, and over here you can see it poked right through our very nice graphene sheet. So the sample was completely destroyed. So we thought stainless steel is probably a great idea because, well, it's stainless. Well, it turns out that if you use this in an atmosphere of 5 millibars, 1-to-1 hydrogen and water at 750 degrees, form these very nice, and it looks very cool. Little filaments, and they are indeed iron oxide. So stainless is not necessarily stainless. One of the first questions that people ask when they see ETEM data is what happens due to interactions with the beam? And that is obviously a very good question. So what we often do is we perform offline reference experiments. So we basically do the experiment, we look at the sample, expose it to the conditions that we expect things to happen at, take the gas back out again, bring the temperature back out, and see if what we expected to happen actually happened without the exposure to the beam. And then redo the experiment with the beam. And also, that's a time issue. Many experiments or many phenomena happen on scales that are not suited for TEM. So usually you can sit in the lab for maybe a day straight, but experiments taking much longer than that are not really feasible unless you have a partner that you can switch with. So moving on to how the gas affects the imaging capabilities of your microscope. This, of course, is a picture of the Tower Bridge in London on a nice sunny day. You don't see many of those in London. You see more of this, where your image is not so nice, and you can barely see that it's a bridge. So what happens in our case? Well, the main effect of having the gas in the microscope is loss of intensity. So over here we try to record just the intensity, no sample in the beam. You can see for the lighter molecules like helium and hydrogen, there's basically no change as you increase the pressure. And this is for these are helium and hydrogen up here. You see just about 5% for hydrogen at the maximum pressure we can have with hydrogen, about 8 millibars. For the heavier gas molecules like nitrogen, oxygen, and argon, you see a much more severe effect. So at 300 this is all at 300 kilovolts. You see, if you go to high pressures, you have only 30% left of your original intensity. Now, there's a big push these days for going to lower acceleration voltages. FEI is pushing the Titan to, I think, down to 30 kV or something like that now. But if you do the same experiment at 80 kilovolts, which is what you see here, you see these numbers are much more severe. You can also see a big drop already for hydrogen and helium. And if you use argon at high pressure, you basically have nothing left. So all of the initial electrons are scattered off the gas molecules and are lost for imaging. But with that said, argon is of course the most severe case, and how often you use argon in the microscope. And second is, you would rarely operate at these high pressures. You would be down in this region. The funny thing with these kind of data is that you can actually determine the mean free path and the scattering cross section. So that's what we did here. And you can see for these heavier molecules at lower acceleration voltage, the mean free path is about the length of the pole piece gap. And this is just again done just by a standard exponential decay fit and assuming an ideal gas. You can see for the hydrogen and helium is not even included for the 300 kilovolts because the the loss is just so little. The more interesting thing is to look at how the contrast is transferred through a gas. And to monitor this, we imaged an amorphous carbon film at various pressures. This might be one of the most boring TEM images you've ever seen because it's just a film in vacuum. You can check the Fourier transform and you see nice tone rings out to high angles. Now we introduce, or you can do a radial intensity distribution and you see all the wiggles, which is something close to the contrast transfer function, but not completely. You can then introduce 17 millibars of argon. You can see the image is a little more dull, the detail is a little more blurry. And when you take the Fourier transform, you see you've lost most of your rings. The defocus should be the same. We can use the aberration corrector interface to monitor the defocus exactly based on the tone rings here. So the defocus on these two images is about the same. And if you do this as a whole series, you can see the black line up here is before the experiment. Then we gradually increase the pressure. You can see at low pressures there's basically no change. When you start to go very high in pressure, you lose your wiggles at high K values. And at very high pressure, you only have the first few of them. And just to convince you that the whole experiment didn't just etch away the whole carbon film, we did another run after we took the gas back out again. That's the red one up here. You can see we can maintain the original contrast transfer. If you plot the step height from wiggle to wiggle in the contrast transfer, you see that you have a much faster decay at high pressure here than you do in vacuum. So you lose your high K information much quicker in a gas than you do without the gas. That more or less brings me to the finish of the first half of the presentation. I just put all the names here of the people who contribute to the second half. I probably left out some. The main people at DTU who does this work is Jakob and Christian and our two PhD students and our former boss, which is now in Jülich. We have a close collaboration with people at EPFL, the CIME department. Quentin Chongru is a master student, a PhD student, and he spends about half his time at ETU and half his time at EPFL. Then we have a close collaboration with Willem van Dorp from the Netherlands, doing this FEBIT, which I'm going to get into in just a little while. Tim Booth at the Nanotech department does all the graphene stuff. And a couple of people from Roya and John from Oslo in Norway, catalysis work, and then we have a collaboration with Pedro Costa from Portugal, doing some Kirkendall effect experiments, and then we still work with the catalyst company Halvatopso, which is located just 2 kilometers north of DTU. So the example I'm going to show you is going to revolve mainly around various aspects of catalysts and fuel cells, formation of zinc oxide wires from Kirkendall effects, and a couple of graphene stories, and then I'll get into this focused electron beam induced deposition as well, which is kind of nanopatterning, quite neat. So one of the first experiments that was done back in the top flow days was we looked at this very nice ammonia synthesis catalyst, which was a ruthenium on boron nitride promoted with a barium compound. And if you look at this, it might not be so obvious, more obvious here. All of these, this is a conventional TM image. And if you notice all of them, it might not be easy to see on this one, but you can see it over here. All of the metal particles are encapsulated by boron nitride. Now, it's quite difficult to understand as catalysis happens on the surface of the particles. It's quite difficult to understand how can this material be active if all the surfaces are covered. And this is the best catalyst ever found for ammonia synthesis. So how could it be active? Because it looked like this. So we said, okay, let's expose it to the reaction conditions that we have in an ammonia synthesis reactor. It's about 3-to-1 hydrogen-nitrogen at about 450 degrees C. And all of a sudden we saw that this layer around the surface disappeared and all of the surfaces became nicely visible. Furthermore, we identified these structures here on the surfaces, which we believed to be the promoter phase sitting on the surface of the active metals. And we were lucky enough to get this published in Science back then. And also we determined the state of these compounds sitting on the surface, and did in fact determine that they were barium-containing compounds. Another story, this was the PhD work of Jakob Wagner. He looked at copper particles on zinc oxide, which is a great methanol catalyst, or the industrial methanol catalyst. And he noticed when it was exposed to a very oxidizing environment, so a mixture of hydrogen and water vapor, the particles appeared very round, and he could identify them based on the lattice spacings. He could identify this as metallic copper. And he made the Wolf construction down here. When he moved to a more reducing environment, he could again identify the particles as metallic copper, but all of a sudden they were nicely faceted. Then he moved to an even more reducing environment by adding carbon monoxide to the environment, and all of a sudden you again saw that they were still faceted, but they were much flatter than before. This is obviously not the same particle, but it's representative particles. Again, you see the Wolf constructions down here. So what happens is that one thing is you absorb these different oxidizing and reducing compounds on the surface, and you change the surface, the relative surface energies of the materials. Secondly, you, in this case, probably reduce the surface of the zinc oxide, making or changing the interface energy of the particle support system. So that way, you would have a much higher degree of wetting in this very reducing environment. And since this was the early days of ETEM, this was also published in Science. This story you might have heard. One of the main problems in a steam reforming reactor is that if your conditions are not good, you can get coke formation or carbon formation, which can have detrimental results because it can start to, when you get these carbon fiber forming inside your pellets, it will crack your pellets and you just end up with a pile of dust at the bottom of your reactor, and then blocks up, and then if you have 100 bars of hydrogen, you're going to have a big bang. So people don't really like to have these carbon formation inside the microscope. Inside the reactor. But it's quite interesting to see how these can form nanotubes. This should be a movie here. So you can see this is a nickel particle in a steam reforming reactor, and you can nicely see how you form a nanotube here. And this is in a 1-to-1 methane hydrogen at a 200 Pascal pressure at about 500 to 540 degrees C. On the other movie here, you see exactly where the individual layers of carbon are formed, progresses through here. But you can see that you decompose your methane at step edges, and you see this front progressing along the surface of the particle, and then you form the individual layers of the nanofiber. One of the most severe deactivation mechanisms in catalysis is sintering, and this is believed to happen through two different routes. One is oscillatory ripening, where you have atoms emitted from smaller particles being absorbed by larger particles. And this way, you have mass transported to the larger particles, and they keep getting larger and larger. And in that way, you lose surface area because your volume to surface ratio becomes smaller and smaller. I won't bore you with the equations this time around, but if you think about this, your particle size distribution that's been shown experimentally should be a distribution with a tail on the small diameter side, because you can imagine, because some particles always emit material, they always become smaller, you're always going to have small particles. On the other hand, the other mechanism is what's called particle migration coalescence, where entire particles migrate over the surface, and when they get into the close vicinity of each other, they merge into a single particle. That has been mathematically shown to give a log normal size distribution with a tail on the large diameter side and a sharp cutoff on the small diameter side. Experimentally, this is almost entirely what we see. This was a study done at Topso last year. And this image might not be the greatest. And the reason for that is that these images were taken at extremely low beam intensity to make sure that there were no beam effects. This was also done on a model system because industrial systems are optimized for catalysis. They're not optimized for electron microscopy. So quite often you have very high surface areas, very complicated structures. So in order to facilitate or to understand the fundamentals of this sintering process, they made a platinum alumina silicon nitride sandwich sample, you can see down here, where you have the silicon nitride, the silicon, and this is again silicon nitride here, and then you have evaporated a layer of aluminum oxide on top of it, and on top of that you have evaporated platinum nanoparticles. That's what you see over here. Now, this is a time-lapsed image sequence. You can see the time here at the bottom. Nice small particles in the beginning. And I made a capital mistake here and didn't put a scale bar on, but these particles are about 5 nanometers. And you can see as time progresses, particles become larger and larger and larger. And if you go in and follow individual particles here, that's what you see. Over here you have the plots of the particle diameter as a function of time of a number of particles. And you can see some of them become gradually smaller, some of them become gradually larger. But you don't see any steps in this. So that's why they concluded from this study that this sintering occurred via the Ostwald ripening process. When you do studies like this, you have to consider a bit what local temperature do you have, because in the furnace type holder that I showed you before, you can only measure the temperature on the outside, but what is the actual temperature in the beam? And if you look in the literature for studies like that, how much does the beam heat your sample? It's difficult to find. I've only found a very few of them. And there's this very nice theoretical treatment by a couple of Russian guys, about 20 years old now, where they have calculated the local temperature increase as a function of current density on the sample. And this actually is the particle size, because there are so many parameters that influence the local temperature. And in the region we are, should be, I think, the middle one. You see there's basically no increase in temperature. We are at least below 10 nanometer particles down here. So they don't see any, if this is true or not. This is a more recent study, where we looked at the particle formation of cobalt particles. This is a Fischer-Tropsch catalyst for making fuel, or liquid fuel. Over here you see the as prepared state, where you have alpha alumina grains with cobalt oxide deposited on it. What we did is we heated it to 600 degrees C in hydrogen, and all of a sudden you can see these patches become individual particles sitting on the surface of the material. And it might not be so impressive in TEM, so what we did is we did it in STEM instead, where you get an atomic number contrast. So you can see over here you have patches here all over the place of, maybe this is the most clear one, of over here of oxide, and over here you see that after treatment in hydrogen, the particles or the patches are broken up into individual particles. And of course you shouldn't take my word for it, because we have all the spectroscopic techniques that we can throw at it. So of course we did yields of this, and this is this region out here, which you see blown up here. So we can put the STEM probe on top of the particle, and we can see there's only a cobalt signal. If had it been oxide, you would also see something down here where you should have the oxygen K line. And just to show it even more clearly, we also put here on the support material where you clearly see the oxygen peak. So we're quite sure that we completely reduced the cobalt oxide to metallic cobalt. Next example is from this our collaboration with the Swiss people, Quentin Jonkel. He works on the anode material of fuel cells, specifically solid oxide fuel cells, which is one of the most promising ones. This is a fairly old plot, so Quentin added the numbers here because the efficiency is considerably better today. A fuel cell looks something like this. It has an electrolyte in the middle, an anode on one side, a cathode on the other side. You stack these up, a number of them, and you can get a potential across, and you can draw power from a system like this through an external load. You supply fuel on one side and then oxidizing gas on the other side. What happens when you supply the fuel is that sometimes you reduce and reoxidize the anode material, and when you do that in cycles, you eventually degrade your fuel cell. You lose the potential, and eventually it becomes pretty bad. And that's what he did here. He cycled it many times and saw that the potential became smaller and smaller. And this is a nickel oxide stabilized zirconia system. So we wanted to see exactly how that happened. This is a flip slice of the fuel cell anode material, where you see, as far as I remember, these are the stabilized zirconia grids. These are the nickel oxide grains. Grains and grains. We also took a diffraction pattern of only one of the nickel oxide. So this is the diffraction pattern, nicely aligned, of a single grain of nickel oxide. So what we did is we ramped the temperature up from about 300 degrees in hydrogen. That's what there we go. You can see the temperature down here, the time. And you can see the ultra stabilized zirconia grains don't change that much, but you can now see that the nickel oxide grains start to become porous. It's because it's being reduced from a nickel oxide to a metallic nickel. Now, we could also do the same thing with the diffraction pattern. Now you can see, hopefully, there we go. In the beginning, again, you see the temperature and the time. You see slightly the metallic nickel peak shows up in the diffraction pattern, and the oxide disappears. So we go from an oxide to a metal. Now that's all good, so why not do it the other way as well? So instead, we took out the hydrogen, put in oxygen instead. Again, you see this is more or less the last frame of the previous movie. We can roll it again. Now we're oxidizing it. If you follow one of the nickel grains, you can see slowly but surely the pores fill up. And you can also see that you have a lot of stress in the ultra stabilized zirconia. You have these lines across the ultra stabilized zirconia. Again, of course, we did the diffraction. And again, you can see slowly but surely the metal disappears. But you'll also see another thing. See the formation of rings, which you didn't have before. Before you had a nice, perfectly single crystalline diffraction pattern. Now you have rings. And that's one of the, just roll this again. Back. That means that you have a polycrystal of nickel oxide at the end, where you started out with a single crystalline grain of nickel oxide. And when you have a polycrystal, it takes up more room than if you have a single crystal, because there are going to be little gaps and holes in it. So that's detrimental for your fuel cell, because all of a sudden then the nickel oxide grains take up more space, and your whole system cracks together because the volume becomes too large. That's basically what you see from an equation for you with that. So next example is this Kirkendall effect, where you form from a solid, you form a wire. This is in collaboration with Pedro Costa from CITECO in Portugal. This is the first and last stage of it. This is zinc sulfide, gallium doped zinc sulfide nanowire that transforms into a zinc oxide tube. You can see it's not a perfect tube, but it has the walls are formed by grains, but you can definitely see that it's a tube. And this is treated at about 6 millibars of oxygen at about 600 degrees C. And here are the individual steps of it. You start out by having your gallium doped zinc sulfide inside a nanotube. As you gradually heat it, you see that it forms grains. And as you have formed the grains, eventually these grains sinter at this temperature and form walls. Had you done this in a reactor at higher pressure, you would probably get a nice tube in the microscope. Unfortunately, it doesn't turn out that nicely. The mechanism that Pedro proposed for this is that you have, again, you have the nanotube here. You have your zinc sulfide in the middle. You have oxygen supplying from through the carbon and from the hole in the tube. You can then slowly but surely form zinc oxide from the zinc sulfide, and you have these grains sitting out here on the surface. And eventually you get a complete tube formed out of this, and eventually these grains will form a nice single crystalline material. We did not have time for that, but we did look at samples that were done in a reactor over a longer time, and they show nice tubes of zinc oxide. Can't skip that one. Graphene, of course, is one of the most interesting materials at the moment. So more or less every group with a microscope are doing some kind of things with graphene. Ideally, this is what it would look like: nice smooth surfaces, nice single layers of graphene, perfectly flat, contamination free. Unfortunately, this is for the most part what it looks like. You have contaminants sitting on the surface. You have jagged edges around the surface here. Residual materials from the fabrication. And this is actually what I wanted to show on this one, is that if you treat your graphene in a low pressure of oxygen at a low temperature, you can burn off all this contamination sitting on the surface. These are both after images, but what you can see is you have nice big patches of clean graphene that you can image. Other thing you can see is these are little silver particles on the surface of the graphene, and this is a movie as well. You can see if you have a high temperature in oxygen, you can see that these particles are quite dynamic on the surface. And this is actually a catalytic reaction occurring. You can see that the particles are slowly but surely eating up the graphene. And just to show you, this is not a single case. I have another one over here. You can see the particles are digging trenches. What you may have noticed is that there's some very characteristic angles between these channels over here. And if you start to analyze them, this is what you get. This is an analysis of post-treated sample. And you can see that the channels are at angles of 60 degrees to each other. The further you go from the sensor here, the longer the change. But you definitely see that they are at specific angles. And you can also see that here. That's of course because the silver particles follow the crystalline structure of the underlying graphene. You can also see here an individual channels where you clearly see these 120 degree angles. If you analyze also the movement of the silver particles, you can start to get some idea about the activation kinetics of the process. So here's an Arrhenius plot of various silver particles at various temperatures, and you can extract an activation energy for the mobility of silver particles on the surface of graphene. And there's an artistic rendition of how it could look, and maybe people could imagine fabricating devices based on this kind of thing. If you could start to control how these particles eat their way through the graphene, and you could that way design a structure. You could maybe design transistors this way. Who knows? Now I've hinted at this feedbit technique for quite a while now. I'll actually get to it. So the goal here is to arrange atom one by one. So this is a quote from a very famous Feynman lecture, I think from 1959, where he said, "What would happen if you could arrange the atoms one by one exactly the way we wanted? Then we could design exactly the device that we wanted." Well, it would certainly enable new research and technology. Fundamental studies would be easier. Quantum computing, atomic wires, atomic switches. We could design everything on an atomic level. Again, catalysis come into it, biochemical sensors, and probably many other things. So that's what feedbit is all about. The acronym is Focused Electron Beam Induced Deposition. And here you see this is a slab of graphene, a few layers of graphene, and you can see these patterns that we wrote on the graphene. The way that it works is that you have your substrate. Oops, there we go. You have a metal organic precursor. In this case, it's tungsten hexacarbonyl that you put into your ETEM at a fairly low pressure. This precursor adsorbs on the surface of the substrate. Then you have your electron beam. Inside the beam, your adsorbed precursor will decompose, and you will form just the metal particles. So what are the capabilities of this? Well, you can write with ultra high resolution. This is a map of the world. See, we are right now down here somewhere. Well, this is pretty small. And this is written by rastering the beam or parking the beam at different positions over the substrate. So you can write stuff like that. This is maybe quite big. You can do it much smaller. You can write arrays of patterns or of dots. You can do lines. And you can do even smaller. What you can see when you go from fairly large dots to fairly small dots is that the statistics become much poorer. So that's one of the things we're working with for the time being. This is written on a self-assembled monolayer, so a carbon substrate, where you can see you wrote two lines here. And the full width, the intensity is a function of how long you park your beam. So this is the high angle annular dark field intensity as a function of how long you park your beam at a given position. So you can see the longer you have your beam in a given position, the higher the signal, so the larger the dot. There's also a function of the thickness of the substrate that you're writing on. This is a 1 nanometer thick substrate and a 31 nanometer thick substrate. And you can see you get almost twice the full width at 75% maximum. So obviously, looking at this, going to thinner substrate is better. So what we tried, of course, is to do it on graphene. And this is one of the ways that you can produce graphene. Put a N-methyl pyrolyline into an ultrasonic bath, centrifuge it, and you can deposit onto your grid. And then you can get very nice slices of graphene that you can write on. And again, using the cleaning treatment that I showed before, you can get nice big patches of clean graphene that you're writing on. And in that way, we wrote very tiny dots. You can see there's a 10 nanometer scale bar, so these dots here are about 1 nanometer big. And if you do it in TEM, you can see, it's not so easy to see, but you can easily see you have little dots of tungsten here. And I'm sure you can imagine you can write various devices on your substrate using this technique. Next study is part of a bigger project here called what we call the CASE project, which is catalysis for sustainable energy. It's kind of a way of next generation energy. We have our design wheel, which is we predict a catalyst which is good for a given reaction by density functional theory. We synthesize it here, we characterize it, and we test it, and then we loop back. So what comes, the input from the various steps go back to into the loop, and we can hopefully modify our catalyst and get something even better. In this case, it's from the alcohol process where we're trying to synthesize alcohols, ethanol, methanol, and ethanol. So basically, yesterday you were feeding your horse with hay. Now we want to put the hay into the car, but we probably have to do some pre-treatment first. Most of the catalyst that comes out of this project are alloys. So we want to try to do the same thing in the microscope and see how stable they are, how they perform, and compare the results that we get from the ETEM with the complementary techniques such as in situ XID. We have actually built an inert transfer system so we can transfer inertly our samples from the XID setup to the ETEM facility. This was one of the catalysts that was supposed to be a very good alcohol synthesis catalyst. It's a copper tin alloy on alumina, and it was very good for a very short time. It tended to deactivate very quickly. This is how it originally looked. So we tried to find out why is it that it deactivates so extremely quickly. So we tried to do a stability test in the ETEM. So we did exactly the same operating conditions, of course, much lower pressure. And what happened is this is a reduction in 1.2 millibars of hydrogen, and you could see that there's severe sintering where the particles are tiny over here. All of a sudden, you have huge particles. So the reason that this catalyst deactivates so quickly is that it's just not stable. You form very large particles in absolutely no time. And this is only a matter of it says right 2 hours. Yeah. Another very promising candidate is copper nickel alloy. In this case, it's on silicon oxide. So what we see what we have is we wanted to make sure that the copper nickel forms different stoichiometries. So what we wanted to see is which kind of material we had. So this is one of these particles, and we have made a particle size distribution of it here. Look closer, and we heard a lot about eels yesterday. So here's the eel spectrum of this material, what we can use to quantify the exact composition of these particles, and also we can use the Fourier transform of the high resolution micrograph to see what compound it was, and it turned out to be copper 1 nickel 1. Same thing we tried to for a nickel gallium system. We tried to do the synthesis in situ in the microscope. First of all, we tried to do it in our situ XID setup, where we deposited the salts in the sample holder, and then heated it up in hydrogen, as far as I remember. And gradually, you could see these nickel gallium phases starting to form as you increase the temperature from the XID. So we said, okay, let's try to repeat it in the microscope and see what happens. So here you have room temperature, 300 degrees C. So this is just the salts deposited onto the nitrates, I think, of nickel and gallium deposited onto a grid, and as you heat it up, you form nice particles. So again, to make sure we knew what we had, we did high resolution imaging of these. We got the FFTs, and we could confirm that this was a nickel 5 gallium 3 phase, and we got the same result from the yield spectrum of the particles. One of the most interesting or unexplored territories of catalysis is the interaction between surfaces and particles, so support surfaces and particles. So we try to make a model system for that because, again, working with industrial catalysts is usually not optimized for electron microscopy because they are complicated structures. So it turns out that magnesium oxide, if you burn a magnesium ribbon in a flame, you get these very nice cubes. So that was the perfect model system for this kind of study, because you had very nice homogeneous surfaces. Here we see such an individual cube. They turned out that they like to be brothers, so there was always a little one on top of a smaller one. And here you see we have deposited, it might not be so clear, but we evaporated little tiny gold particles onto the surface. You can see them as well down here. You can see that the cube is nicely aligned. Now what happens when you start to put this in the microscope and look at it is that the surfaces become rough. You see these pillars starting to grow. This has been reasonably aligned. So we wanted to see what kind of effects do different changes in the environment have. What happens if you have the particles, if you don't have the particles, if you change the vacuum, or if you change the beam current density. So that's what we're seeing here. First of all, we got one. This is without gold particles. Over here you have with particles. So you see everything else is identical. The residual chamber pressure and the beam current density is the same. Over here, absolutely nothing happens. Over here, you see these magnesium oxide rods growing as a function of time. So okay. Again, this is the same reference movie as before. Now what we did here is, this is at a lower pressure, so 1 order of magnitude lower pressure. Otherwise it's the same system. And you see, you don't find these growing. So you need to have just a little bit of water vapor in your cell to make these wires grow. Now we have same chamber pressure. Now we have a lower beam current density. And again we see that we also need the beam to have it happen, because again the same reference movie over here as before. But over here only very little growth when we decrease the beam current density. So this is definitely a beam, gold, and atmosphere driven process. And I think this is the last example as far as I remember. This is from my own work, where we study sintering of particles as well. In this case, it's a model system consisting of gold particles on a graphene substrate. Again, these particles just evaporated onto the substrate because you get a nice, with graphene, you get a nice two-dimensional substrate, so you can easily image all the particles. And this is at room temperature. You see it's just wiggling a bit around its own axis, and if you extract a few stills, you can see the atoms here on the surface. The surface configuration is changing a little bit from frame to frame, but basically it's not moving. You see it twisting a little bit in the end, but that's the graphene buckling a bit. Now, if you increase the temperature and put a bit of hydrogen in there, all of a sudden things look a lot different. You see, I've outlined an area up here. You can see this little particle is gradually being sucked in by the larger particle. And as far as I remember, up here you see the particles are sucking up each other. I extracted a few frames down here. And I also made a zoom of this area here. You can see this much clearer. This runs in loops, so it doesn't spit the particle back out again. It really just absorbs it. So what we see from a movie like this is, let me go back to this one, is that you actually see both Oswald ripening happening. This particle is gradually getting smaller, whereas what's happening up here seems to be the whole particle being sucked in more or less at once. So you see both particle migration coalescence happening and Oswald ripening happening under the same conditions. So beam effects is one of the most severe things when you are discussing environmental TEM. First of all, the electrons can ionize the gas molecules, making them much more reactive, because all of a sudden you have ions and not atoms. Surfaces can be etched by reactive gas atoms and ions. There's a very nice account of this in this is actually Søren Simonsen's paper. This is from the Stihelvig group at Topsø, where they did a very nice analysis of the beam effects on this system. There's also the paper that I quoted before, the Russian guys, which have done a very nice theoretical application or determination of this. There's also knock-on damage, of course, also in the atomic structure, and sample ionization due to exposure to the beam. But you could also have a benefit of having gas in there. You could have some decharging. This is actually what you use for your advantage in an SEM. If you have a very charging sample, then you would put a bit of gas in there and you can get rid of the charge. In the present study here, that was the gold particle I showed before. We tried to increase the beam current density with a factor of 10, and we didn't see any particular behavior or change in behavior. So some of the conclusions from this is, from the gold work, I think I'll skip this one for tomorrow actually. Go straight to the challenges here. One of the severe challenges in ETEM is to detect reaction product from in situ experiments. You have such a tiny amount of catalyst in there, you have such a tiny amount of gas flowing into the system. So the amount of product molecules that you make is very minute. Second thing is to deconvolute the beam effects from what we're actually seeing. If we can understand what the beam does, then maybe we can also deconvolute it from our experimental observations. Sample heating and local temperature, well, it's okay that we're measuring on an external device, we're measuring the temperature, but what is actually the real local temperature at the position of the beam? Transient phenomena are quite difficult to observe due to drift. That might to some extent be fixed by using these MEMS device holders. So if you're using this lab, you should definitely try that out. And obviously, high pressure, we can only go to a limited amount or a limited value for the pressure. And some people do insist on using balanced gases when they come to us, but again, you don't want to do that. And even the balanced gas, which is quite often nitrogen, can have some effects on your sample. The more challenges, again, sample heaters, detector efficiency. If we want to really minimize the beam effects, we need to have more efficient detectors. That's one of the things that's really being developed at the moment, and you'll see that direct electron detectors are really on the move at the moment. Sealing technology, we might want to go away from using O-rings because they do leak, but it's still the standard way of sealing your system. You always need to do complementary in situ techniques to verify that what you're actually observing is the real deal. That's the same as before. Also, one take-home message here, or a couple of take-home messages. Think your experiment through before doing an ETEM experiment. Is it feasible to do it under the conditions and timeline that you have for ETEM? So, if possible, do ex situ reactor experiments prior to ETEM experimentation. You have to be careful. Very large amounts of data can be generated quickly. Consider if you use the full CCD on a standard microscope is a 2K by 2K CCD. So each image, if you record it in digital micrograph, is 16 megabytes. If you want a time resolution of 500 milliseconds, you're generating 16 megabytes or 32 megabytes per second. So just a 1 minute movie is a big thing. Other thing you have to do is modifying your TEM to ETEM capabilities. It doesn't affect the resolution. Our microscope works perfectly well as a standard microscope. The only thing is that the high angle angular dark field signal is limited a little bit by the pumping apertures. As you can see here, you still get quite nice resolution in standard work. 0.9 resolution, 0.9 angstrom resolution on a silver particle. And I think I will leave you with this slide, which is a couple of the key references, which shows you a lot about ETEM. This is the Boyce and Guy ultra microscopy paper from 97, which shows the design of the differentially pumped column. That's a very nice review by Renu Sharma in Microscopy and Microanalysis from 2001. And then there's an old handbook which has a section devoted to ETEM. Abaya Darcy wrote a very nice paper together with the Topso people, also a review paper on the state of the art of E10. And there's a whole volume of Journal of Material Science devoted to in situ techniques, which shows a lot of this. And I think that was the end of it. Thank you for your attention.